Let's take on some questions from the chapter Bending of Beams. The flexural rigidity of a cantilever beam is assumed to be constant over the length of the beam shown in figure. Okay, so flexural rigidity, that is EI, is constant. If a load P and a bending moment PL by 2 are applied at the free end of the beam, then the value of the slope at the free end is. Okay, so we can solve this by superposition method. Okay, what is that? Superposition method. What is that? That I can find the individual slopes by this load first, and then by the moment that has been applied at the free end, and then we can add both of them. So due to this load, this point load at the free end of the beam, the slope at the free end will be equal to PL square by 2EI. This is the standard result that we remember. Plus there will be a slope due to this moment, which is PL by 2, moment is given, and the slope is actually at the free end, it is equal to ML by EI. Okay, so what is M? M is PL by 2 here, so this becomes PL square by 2 EI. So total slope at the free end will be equal to sum of slope by this point load plus the sum of slope by this moment, which is PL square by 2 EI plus PL square by 2 EI, and that becomes equal to PL square by EI. Okay, so option B is the answer. Next question. A cantilever beam of length L with the uniform cross section, cantilever beam is given, length L is given, uniform cross section and flexural rigidity EI is loaded uniformly by a vertical load W per unit length. Okay, so the cantilever beam is given, length given is L, and it is loaded uniformly by this load W per unit length. Okay, the maximum vertical deflection of the beam is given by, okay, so this is the standard result that you remember, which is WL4 by ATI. You remember this result, or if you want to derive this result, you can take a cross section at a distance x, take a cross section, and then you can integrate and find the deflection. Okay, so but this is the standard result that we remember, and it will save your time in the exam. Next question. Consider a simply supported beam of length 50h with a rectangular cross section of depth h and width 2h. Okay, the beam carries a vertical point load P at its midpoint. So the ratio of the maximum shear stress to the maximum bending stress in the beam is, okay. So let's draw a schematic diagram of the beam. It carries a vertical point load at its midpoint. Okay, so this is P. L is 50h, and the cross section is rectangular with depth h and width, rectangular cross section 2h. This is x-axis, this is y-axis. Okay, now for a rectangular cross section, we know that maximum shear stress is equal to 3 by 2 of tau average. Okay, and tau average, that is average shear stress, is equal to P by, but here P will be P by 2. How? This we get from shear force diagram, because you will calculate the reactions here. Here it will be P by 2, here it will be P by 2 again. So the maximum shear force in the entire beam will be equal to P by 2, when you draw the shear force diagram. And area is 2h into h, because this is rectangular cross section, so 2h is the width and h is the depth, so 2h into h is area. So this becomes 3 by 2 into p by 2, in the denominator it will be 2h square, so this becomes 3 by 8 p by h square. This is tau maximum. Okay, and if you have to find the maximum bending stress, this we can find out by the bending equation, sigma b maximum which will be equal to maximum moment upon z, where z is equal to moment of inertia about the neutral axis of the beam upon this distance y, which is equal to h by 2. Okay, so moment of inertia about neutral axis, this beam is bending about x-axis. Okay, so moment of inertia will be equal to bh cube by 12. Here b is 2h, h cube by 12. Okay, so when you solve this, this will be h cube by 3. And maximum moment, what will be the maximum moment? Okay, beware that the maximum moment here will be PL by 4, not PL by 2, because the because the reaction here is P by 2, and when you will draw the bending moment diagram of this beam, you will know that the maximum moment in the beam comes out to be PL by 4. Okay, you can draw the you can draw its bending moment diagram. It's very simple. So when you draw this bending moment diagram, you will get maximum moment that will be equal to PL by 4. So put these values here, sigma b maximum, that is maximum bending stress, which will be equal to PL by 4, and this is h cube by 3. So L, what is the length of the beam? Length of the beam is 50h. Okay, so this becomes this will be P into 50h upon 4 h cube into 3, so this will be h square, and this gets cancelled out by 25 by 2. This is 25, this is 2, so this will be 75 p by 2h square. This is the maximum bending stress. Okay, now all we have to do is take the ratio of the maximum shear stress to the maximum bending stress. So 3 by 8 p by h square divide by 75 p by 2h square. When you solve this, the value, the answer will be 1 by 100, which is 0 0.01. Okay, because p by h square gets cancelled out, so it is a constant, and the value is equal to 0 0.01. Check the options. The options, D is the answer. Okay, so all you have to do is draw the SFD and BMD if you are not getting the value directly. Okay, so next question. A force P is applied at a distance x from free end of the beam. I think some typo is there, as shown in the figure. Okay, what would be the value of x so that the displacement at A is equal to 0? Okay, so when you see at this cross section A, what you see is, due to this load P at a distance x, there will be a load P at a point A also. Great, but this P is also exerting a moment. Okay, so when you see, there will be a moment at A also due to this load P, and in the anti-clockwise direction, and the moment will be equal to P into L minus x, because this distance is L and this distance is x from where this load has been applied, so the distance becomes L minus x. Okay, so P into L minus x will be the moment due to this load P, which will be acting at point A. Okay, now the deflection due to this vertical load P will be in the downward direction, but the deflection due to this moment p into L minus x will be in the upward direction. So when these deflections will be equal, the displacement at at cross section A will be equal to 0. Okay, so due to this load P, due to this vertical load P, the deflection, we know the formula, that is PL by 3 EI, and due to the moment, the deflection in the upward direction will be equal to ml square by 2 EI with a negative sign, and it is equal to 0 because we have to find the value of x so that the displacement at A is equal to 0. Okay, here m is equal to what? M is p into L minus x. Okay, now you can solve it. PL cube by 3 EI is equal to p into L minus x, L square upon 2 EI. EI gets cancelled out, L square gets cancelled out, p and p gets cancelled out. So this will be L by 3 is equal to L minus x by 2. Okay, when you solve it, you will get x is equal to L by 3. Okay, so the option will be C, 0.33 L. Okay, yeah, so this was a simple question again. Okay, let's move on to the next question. A frame is subjected to a load P as shown in the figure. The frame has a constant flexural rigidity EI. Okay, the effect of axial load is neglected. Okay, note this line. The effect of axial load is neglected. The deflection at point A due to the applied load P is. Okay, so whenever you see these type of questions, try to solve these type of questions by strain energy method. Okay, so strain energy method is deflection at the point where the load is acting is equal to del U by del P. Okay, so the load is acting here at A, so deflection at A will be equal to del U by del P in the entire beam. Like, you have to find the strain energy in the entire beam, and then you will differentiate it, partially differentiate it with this load P. Okay, so find the strain energy in the entire beam and then partially differentiate it with the load which is acting. Okay, so let this be B and the fixed point be C. So can I find strain energy in AB? Yes, I can, because strain energy in AB will be equal to m square xx dx by 2 EI. What is mxx? This is the moment at a cross section xx from a distance x due to this load P. Okay, so at a distance x, at a cross section xx, the moment due to this load P will be equal to px. Okay, put the value here. So this is px square dx by 2 EI. Okay, you have to integrate it from 0 to L because the length of this beam is L. Okay, length of AB is L. So this is p square x square 2 EI, integration from 0 to L dx. Okay, when you solve it, strain energy in AB will be p square L cube by 6 EI. Okay, similarly we can find out the strain energy in BC. Okay, this is C, this is B. How? Now, due to this load P at A, there will be a load P at point B also. Okay, if you see at cross section B, but there will be an additional moment at cross section B due to this load P, and the moment's value will be equal to PL. Okay, so this will be PL. Now this line plays an important role. The effect of axial load is neglected, so you have to actually neglect the strain energy value due to this axial load P on the bar BC. Okay, you have to only take the strain energy due to this moment. Okay, so UBC is equal to, again, 0 to L integration m square xx dx by 2 EI. What is mxx? I have told you, the moment at a cross section xx from a distance x. Okay, so moment here is constant and the value is equal to PL. So put the value that is which is equal to PL square by 2EI dx 0 to L. So you solve it, UBC is actually equal to P square L cube by 2EI. Okay, now the total strain energy will be equal to UAB plus UBC, okay, which gives me total strain energy which is equal to 4 P square L cube by 6EI. Okay, now the deflection at point A due to the applied load P is partial differentiation of this strain energy function with respect to P, and that will give me 8 PL cube by 6 EI del U by del P, which is equal to 4 by 3 PL cube by EI, and this value is equal to the deflection at point A due to this applied load P, and the option is D. Okay, so strain energy method comes handy in these type of questions. Okay, next question. A cantilever beam with the flexural rigidity of 200 Newton meter square is loaded as shown in the figure. Okay, flexural rigidity, that is EI, is equal to 200 Newton meter square. The deflection at the tip of the beam is, okay, so you have to find the deflection at the free end in mm. Okay, beware, you have to write the answer in mm, not in meters. Okay, so let's just draw a schematic diagram of this, rough schematic diagram of this beam. The load acting here is 500 Newton. This is 0.05. Let this be free end be point A. The load, the point where the load is acting, let that be point B. This length also becomes equal to 0.05 meters. Okay, this is 100 mm, this is 50 mm, this is also 50 mm, that is 0.05 meter. Okay, so when the load is acting at midpoint, the deflection will be like this, but after this point B, the beam will be a straight line. Okay, it's difficult to draw here. This is bending like this, but after point B, as no load is acting in the portion AB, this will be a straight line. Okay, this is a straight line. This is a curved line, but after B, as no load is acting in this section AB, this will be a straight line. Okay, so let this angle be theta, and the deflection, this be y. Okay, so can I say that the total deflection at A will be equal to deflection at the point B due to this 500 Newton load plus theta into L plus this additional distance y. Okay, so this is delta B and this distance is y, so the total deflection at A is equal to delta B plus y, and this is a straight line because no load is acting, so tan theta is equal to y by L, and as theta is small, I can write tan theta as theta, which is equal to y by L, so y becomes theta into L. Okay, and now we know the values of the deflection when a point load is acting at the free end. Okay, the value of the deflection is, suppose a point load P is acting, the value of deflection at point A will be PL cube by 3EI, and the value of slope is equal to PL square by TEI. 2EI, sorry. 2EI. We know these formulas. So at point B, due to 500 Newton load, delta A is equal to delta B plus theta into L. Delta B will be equal to PL cube by 3EI. What is P here? P is 500 Newton. Let 0.05 meter be L. Okay, so this will also be L. Okay, so plus theta PL square by 2EI into L. Okay, so P is 500 Newton, L is 0.05 meter cube by 3 EI plus PL cube by 2 EI. So P is 500 Newton, L cube, that is 0.05 meter cube by 2 EI. Okay, so this is actually 5 PL cube by 6 EI. So 5 PL cube by 6 EI. EI is 200 Newton meter square. Solve it. You will get the value equal to 2.604 into 10 raised to the power minus 4 meters. But beware that you have to put the value here in mm. So the value which you have to put will be equal to 0.2604 mm. See, the deflection is so small, so small. That is why I have taken tan theta is equal to theta, because actually the deflection is very, very small. So 0.2604 mm is the answer. Okay, so the key point here was that this will be a straight line after cross section B, because no load is acting in part A and B. Okay, thank you.